Hi everyone. Imagine you're packing for a trip with a limited suitcase and you want to fit every essential item, clothes, gadgets, toiletries, using the fewest packing cubes possible. That's basically the set cover problem, selecting the smallest number of sets so that every element in your universe is covered. Today we'll define the problem formally, see how it shows up in real-world tasks like resource allocation and network design, and learn why it's such a computational challenge. By the end, you'll have both the theory and practical strategies researchers use to tackle set cover. Let's dive in. Now, let's visualize the set cover problem in action. Here, our ground set is shown as teal dots, and we have a family of subsets outlined and labeled S through S. Our goal? To pick the smallest possible sub-collection of these sets so that every dot lies inside at least one chosen outline. Notice the overlapping regions. Some dots fall into multiple S's, while others belong to just one. The real challenge is deciding which subsets to include so that no element is left out, all while keeping the total number of sets as low as possible. Now that we've seen what set cover asks for, let's turn to vertex cover and show how to reduce it in polynomial time. Recall the vertex cover problem. Given an undirected graph G equals VE and an integer k, we ask whether there exists a subset W of V with equals k, such that every edge in E has at least one endpoint in W. In our example, the orange nodes form a valid vertex cover. Each edge touches at least one orange node, while the yellow nodes lie outside the cover. This formulation is exactly what we'll use as the starting point for our reduction to set cover. Next, we'll build the corresponding set cover instance step by step. Building on our vertex cover formulation, we now translate it into a set cover instance by treating each vertex as a set and each edge as an element. Concretely, for every vertex V in V, we create a set S underscore V that contains exactly the edges incident on V. We leave the size parameter unchanged, setting k equals k, so any vertex cover of size k corresponds directly to a set cover of size k. Because this construction only involves listing each edge under its endpoints, it clearly runs in polynomial time. Now that we've shown how vertex cover reduces to set cover, the set cover problem stands out as one of the core challenges in combinatorial optimization, right alongside SAT and the traveling salesman problem. What really sets it apart is its universality. Countless other problems, from resource allocation to network security, can be restated as set cover instances. By reducing those problems to set cover, we tap into a rich toolbox of algorithms and approximation techniques, turning once intractable tasks into solvable ones. Now, building on our discussion of set cover, let's turn to the dominating set problem. At first glance, it resembles the well-known vertex cover problem. Formally, we're given a graph G equals VE and asked to choose the smallest possible subset V, called a dominating set, so that every vertex is either in V or adjacent to at least one vertex in V. In its decision form, we simply ask, does a dominating set of size k exist? One common way to prove its difficulty is by reducing from vertex cover. On the right, you see an 8-vertex graph. The 4 interior nodes form a dominating set because each corner node sits next to at least one of them. No corner is left undominated, yet we've used only 4 vertices. This example really captures the essence of the problem. Cover the entire network with as few watchtower nodes as possible. This slide illustrates the feature selection problem. On the left, we have 12 samples, S through S, and 4 candidate features, P to P. Each colored square tells the story. Yellow means a feature is present in that sample. Dark red means it's absent. Our task is to pick as few of these features as possible, so that every sample remains uniquely identifiable. In other words, we want the smallest set of columns, whose combinations of presences and absences distinguish all 12 samples. On the right, you see one such optimal subset. Even with just those feature indicators, no 2 samples share the same pattern. By narrowing down to the most informative features, we simplify our models, cut computational cost, and focus on what really matters. Building on that, here we see 12 candidate features, S1 through S12, measured across 4 patterns, P1 to P4. Each colored box shows whether a feature is active under a given pattern. Our goal? to choose a small subset of features whose activation patterns are all distinct, so no two patterns look the same. By inspection, features S3, S4, and S5 do the trick. On the right, you can see their combined response vectors for P1 through P4. Each pattern lights up a unique 3-feature signature. In other words, with just S3, S4, and S5, we perfectly distinguish all 4 patterns while cutting out 9 redundant features. Building on our earlier example, here we have 12 candidate SNPs evaluated across 4 haplotype patterns, P through P. Each colored square represents the allele state of a particular SNP under each pattern. Our objective remains to choose a small subset of SNPs whose combined allele profiles uniquely distinguish all 4 patterns. On the right, the slide shows what happens if we pick SNPs S, S, and S. Notice that P and P share the exact same 3 SNP profiles, so you couldn't tell them apart. The inset graphic, which crosses out P and P, really drives home that ambiguity. The key takeaway? Any valid feature set must separate every pattern. If 2 patterns look identical, that selection simply won't work. Building on that idea of selecting minimal distinguishing features, here we see a matrix of 12 candidate feature sets, labeled S through S, alongside our 4 patterns, P through P. Each yellow square marks where a given feature set covers a pattern, while a red or blank cell means it doesn't. Our goal is to pick as small a collection of these sets as possible, so that every pattern is covered at least once. On the right, we've highlighted the combination of S and S. Together they cover all 4 patterns. S handles P and S picks up PP and P, showing a valid feature selection. However, finding the absolute smallest such collection is nitrogen monophosphide hard. In fact, it's exactly the classic set cover problem under a new name. Building on that insight, we now reframe our minimum test collection task as a classic set cover problem. On the left, you see 4 test patterns, P through P, and 12 samples, S through S. Each colored cell indicates that a given pattern detects its corresponding sample. Our goal is to choose the fewest patterns whose combined detections cover every sample. In other words, treat each pattern as a set of samples it hits, and then find the smallest number of these sets whose union includes all 12 samples. This reduction lets us leverage well-known algorithms and hardness results for set cover to tackle our original testing problem. Building on our previous discussion, let's walk through a concrete set cover example. At the top, you see a table of 4 candidate sets, S through S versus 4 elements. P to P yellow squares show which elements each set contains. To turn this into a set cover instance, we list every unordered pair of elements, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4, as items that must be covered. Below, each set size is connected by edges to exactly those pairs formed from its elements. For example, S covers 1, 2, 1, 3, and 2, 3, while S covers 1, 3, 1, 4, 2, 3, and 2, 4. Our goal is to pick as few sets as possible so that every pair appears at least once. In this small example, selecting S and S already covers all 6 pairs, proving that just 2 subsets suffice to cover every pair of elements. Now that we've framed our problem as a set cover instance, let's explore a classic greedy algorithm. 1. Initialize U to be X, the element still to cover, and let C be empty, our chosen cover. 2. While U isn't empty, pick the set S in F that maximizes intersection, i.e., covers the largest number of yet uncovered elements. Remove those newly covered elements from U, add S to C. 3. Once U is empty, return C. This simple greedy procedure runs in time polynomial in AND. But the natural question is, how close to optimal is the cover it produces? Next, we'll analyze its approximation guarantee. To see this idea in action, let's consider a classic set cover instance. 18 elements shown as green dots, and 6 candidate subsets labeled S through S, each outlined. On the right, you'll find 2 covers. The optimal cover uses just 3 sets, S, S, and S, to cover every element. By contrast, the greedy rule picks the largest available set first, that's S, then proceeds with S, S, and finally S, ending up with 4 sets. This simple example shows how a straightforward greedy choice can miss the smallest possible cover. Building on that example, let's see how we assign costs in the greedy set cover algorithm. Each time the algorithm picks a set, it incurs a unit cost of 1, which we then spread evenly among the elements that set covers for the first time. In other words, if an element X is covered for the very first time in the ith selected set S, we assign it a cost C equals 1 divided by the number of newly covered elements in S. Mathematically, C equals 1, previously covered elements. This way, every element picks up its fair share exactly once. Building on that cost assignment idea, we give each selected set a unit cost and share it equally among the elements it covers. The very first time an element X is covered, we record its cost C, and we never charge X again. If C is the collection of sets picked by the greedy algorithm, then the total number of sets is simply the sum of all element costs, equals element of XC. Building on that result, our next step is to bound the total cost produced by the greedy algorithm. We start by assigning each element XA cost C exactly once, right when it's covered for the first time. Now let C(X) be an optimal set cover. Because every element X must lie in at least one set of C times, each cost C also shows up at least once in that optimal solution. Putting it all together, the greedy cost, which is the sum of all C, can't exceed the sum of those same costs counted over every set in C in formula form. C equals element of X, C is less than or equal to underscore S, element of C, asterisk underscore X, element of SC. Building on our previous inequality, let's start by expressing the cost of our greedy solution C as the sum of its individual element costs, equals n area summation over X in X of C. Now, since every element X appears in at least one set of the optimal cover C times, we can bound this sum by rewriting it as a double sum over sets in C times is less than or equal to n area summation for S and C, n area summation for X and S of C. Our ultimate goal is to show that this greedy cost is at most a constant factor times the optimal cost, asterisk. In other words, we'd like to prove is less than or equal to alpha asterisk. To get there, we need to collapse that inner double sum into a single term. Concretely, we look for a uniform bound M such that for every set S in C time, down, n area summation for X in S of C is less than or equal to M. If we can establish that, then is less than or equal to S element of C asterisk X, element of SC is less than or equal to S element of C asterisk M equals MC asterisk, and that constant M will serve as our approximation factor alpha. Building on our previous bound, let's now prove that our greedy solution achieves an O log n approximation. First, we show that for any set S, the total charge element of SC is bounded by the harmonic number H equals 1 plus 1/2 plus 1/3 plus 1. Next, we invoke 2 key lemmas to extend this bound to the entire cover C. Lemma 2 establishes that the size of C is at most the sum of H over all chosen sets. Then lemma 1 observes that the worst-case harmonic term H grows only as O log n. Putting these results together gives is less than or equal to asterisk log n, which completes the proof of our approximation factor. Now, lemma 1 introduces the nth harmonic number, h of n equals 1 plus 1/2 plus 1/3 plus 1 slash n, and claims that h of n grows on the order of log n. Why is that? We group the reciprocals into blocks whose sizes double each time. Block 1, 1. Block 2, 1/2, 1/3. Block 3, 1/4, 1/7, and so on. In each block, every term is at most the first term, so the whole block sums to, at most, block size times first term is less than or equal to 1/2. Since there are about log n such blocks, we get dot h of n is less than or equal to 1 plus log n, 1/2 equals O log n, dot, proving the desired bound. Building on our previous regrouping idea, let's restate lemma 1. The n-th harmonic number h of n grows on the order of log n. We define h of n as the sum of reciprocals from 1 up to 1/n. To show that h of n equals O log n, we partition these terms into blocks indexed by powers of 2. In the ith block, which runs from k equals 2 caret I to k equals 2 caret I plus 1 minus 1, each term is at most 1/2 caret I, and there are fewer than 2 caret I such terms, so the entire block sums to at most 1. Adding up all blocks from I equals 0 up through about log n gives a total of at most log n plus 1, which establishes the desired logarithmic bound on h of n. Building on that logarithmic bound, let's define hn, the nth harmonic number, as 1 plus 1/2 plus 1/3 plus 1n. Using lemma 2, we bound the size of our computed cover C by the sum of h over all sets S in the optimal cover C time. Then, by lemma 1, each h is at most the maximum harmonic value, and since hn grows on the order of log n, it follows that is less than or equal to C asterisk O log n. Building on our previous discussion of harmonic bounds, lemma 2 tells us that for any set S in the optimal collection, the total cost assigned to its elements, denoted element of SC, is bounded above by the harmonic number h. Here's why. As the greedy algorithm picks sets one by one, we keep track of how many elements of S remain uncovered. Define .u equals. U equals S union S union, union S. So U is the number of uncovered elements after I choices. We continue until the smallest index k with U equals 0, i.e., all elements of S are covered. This decreasing sequence, U, lets us bound each marginal cost at each step, and when you sum those bounds, you get exactly H. Building on that, let's now track how many target elements remain uncovered as the greedy algorithm picks sets. Define U as the size of S minus the union of the first I chosen sets, so U equals U is what's left after selecting S, and in general, U equals union S. Next, we charge each newly covered element, XA cost, C equals 1, S union S, underscore I1, where I is the step at which X gets covered. Summing over all X and S, the total cost telescopes into C equals underscore, I equals 1, U underscore I1, U. For I is off as union S underscore I1, where U underscore I1 by U counts how many elements we cover in step I, and the fraction is the per element cost at that step. This neat decomposition sets us up to bound the total cost by a harmonic series. Building on that decomposition, the top formula expresses the total cost of the greedy cover as a sum of marginal contributions. Each term, UU, counts how many previously uncovered elements the ith chosen set S picks up, weighted by the reciprocal of its new coverage. S underscore less than I. S. Below, you see a universe of green points with 6 candidate sets S through S. In reality, the minimum cover uses just 3 sets, S, S, and S. But the greedy rule first grabs S, then S, then S, and finally S, ending up with 4 sets. This concrete example vividly illustrates how the greedy algorithm can overshoot the optimal by a logarithmic factor, exactly as our upper bound formula predicts. Building on our upper bound formula, let's formalize how we charge costs across the greedy iterations. First, define U as the number of elements still uncovered after the algorithm has picked sets S through S. Our aim is to bound the total cost element of SC by rewriting it as a sum over each greedy step. At the ith step, the algorithm selects set S, which covers exactly U new elements, We then charge each of those newly covered elements a share of the set's cost, namely 1 S union S. Here's the key insight. In every round, the greedy choice S covers at least as many uncovered elements as any other candidate set S could at that moment. Formally, S union S is greater than or equal to S union S equals U. Because of this, each per element charge 1 is at most 1 U. Summing over all k iterations gives us OK underscore I equals 1 caret k UU 1 an lis 1 slash U. That sum telescopes into the familiar harmonic series, demonstrating that the greedy solution costs at most h underscore n times the optimum. Continuing from our last step, we now focus on a fixed set S and define U as the number of its elements that remain uncovered after the greedy algorithm has picked sets S through S. Using this notation, we can express the total cost charged to S as underscore I equals 1 is 1 S union S. The key inequality here is that at every iteration, the greedy choice S covers at least as many new elements as S would at that point. Otherwise, S would have beaten S to the punch. This observation explains exactly why the algorithm always picks the set that covers the maximum number of yet uncovered elements. Continuing from our previous slide, we let you denote the number of elements in our target set S that remain uncovered after the greedy algorithm has selected I sets. Our goal is to bound the total cost assigned to elements of S, which we express as the sum over X in S of C. First, we group those costs by the step at which each element is covered. At step I, exactly U new elements of S become covered, and each of those elements incurs cost at most the reciprocal of the number of newly covered elements in the set chosen at that step. In other words, underscore X element of SC is less than or equal to underscore I equals 1 caret K UU fex 1 S underscore J less than I S. Next, notice that the denominator esh underscore J less than I S is always at least the number of uncovered elements of S at step I1, namely U. Replacing the denominator by U gives underscore X element of S. C is less than or equal to underscore I equals 1 caret K U cat 1 slash U. This telescoping sum of WU leads directly to the familiar harmonic bound that underpins the logarithmic approximation guarantee of the greedy set cover algorithm. Building on our previous telescoping insight, we now upper bound the total cost C by a single telescoping sum over K stages. C is less than or equal to UU 1U. Observe that each difference, UU, simply repeats the term 1/U that many times. We can therefore rewrite this as a double sum, 1/U. Since U is greater than or equal to U implies J is less than or equal to U, we're free to relax each 1/U to 1/J. That gives us dot 1/J, which is precisely a truncated harmonic sum, i.e. the difference H underscore U, and that completes our harmonic sum bound on the total cost. Building on the previous slide, we now bound the total cost over S by organizing it into K phases and expressing it as a sum of reciprocals. As shown on the left, writing C is less than or equal to 1/J. In the next step, we rewrite that double sum in telescoping form. For each I, we take the harmonic sum up to UH underscore U and subtract the harmonic sum up to UH underscore U. This cancellation lets most terms drop out when we add across all I, yielding a much cleaner overall bound. Next, we'll see exactly how this collapses into the difference of two harmonic numbers. Building on our last step, we now upper bound the total cost element of SC by rewriting it as a double sum. We sum over each phase I equals 1 to K, and within that over j from u plus 1 up to u of 1 slash j. Observe that this inner sum is just the difference of two partial harmonic sums. Underscore j equals u plus 1 caret u1 slash j equals h view minus h view. Pulling that out gives us underscore I equals 1 caret k h view minus h view. If we expand those terms, hu plus hu plus hu underscore k1 hu. Everything neatly telescopes, leaving just hu minus hu minus hu. And that's exactly the bound we were aiming for. Now, building on our previous telescoping insight, we bound the total cost over all elements x element of S by writing it as a double sum of reciprocals. Element of SC is less than or equal to underscore I equals 1 caret k underscore j equals u plus 1 caret u underscore I1 1 slash j. Observe that each inner sum from j equals u plus 1 to u underscore I1 can be expressed as the difference of two partial harmonic sums. Underscore j equals 1 caret u underscore I1 1 slash j minus underscore j equals 1 caret u1 slash j equals h of u underscore I1 minus h of u. When we add these differences for I equals 1k, all the intermediate hu terms cancel out in a telescoping fashion, leaving us with hu minus hu. Since u equals and u equals 0, this simplifies to h. In other words, the total cost is at most the STH harmonic number, h. Now that we've bounded the cost of any set by its corresponding harmonic number, let's dive into our approximation analysis. First, recall that for any set S, the total element cost element of SC is at most h. Next, we compare the cost of our greedy solution C to that of an optimal cover C, DOM. Summing element of S, C over every S in C, DOMs, and applying the harmonic bound gives underscore S element of C asterisk. Element of SC is less than or equal to underscore S element of C asterisk. H is less than or equal to C asterisk. Max underscore SH. Since H grows on the order of log n, this establishes that the greedy algorithm is guaranteed to produce an O log n approximation. Building on our previous bound, the greedy algorithm guarantees an O log n approximation for the set cover problem. In other words, it will pick at most a factor of log n more sets than an optimal solution. And crucially, this performance guarantee scales with the input size. As n grows, the worst-case gap only grows logarithmically. Building on that, this slide wraps up our discussion with two key takeaways. First, among all approximation methods for the set cover problem, the simple greedy strategy still offers the strongest theoretical guarantee. Strongest here, meaning it achieves the tightest proven bound. Second, despite this optimal bound, greedy remains primarily of academic interest. In real-world applications, a variety of more sophisticated or specialized algorithms have emerged to deliver superior practical performance.